Hello. Now we'll study the current density. As you can see, this current density is defined by J and there is a vector sign. So this is a vector quantity. And as the name suggests, it's a current density. But density we don't calculate over to the volume. Here we calculate corresponding to the cross-section area. And the direction of current density is always taken in the direction of current flow. So if let's say this is a conductor, and in this conductor if the current is flowing in this direction, I current is flowing in this direction. Okay. So here I'm taking that I current here. So here the Di, for the small element, the current Di passing through this small element is defined as J dot ds. Okay. Now you can see here, when we talk about the J dot ds, this ds can be in any direction. So one thing we have to remember here is when we will taking the component of ds, this J is always along the current. This J is always along the current. So this value we will write it as J ds cos theta. So this value we can say this Di is equals to mod of J, the current density, multiplied with this ds is component of ds along J, and along J is the direction of current. So basically we have to take the component of area while calculating the current. Component of area we have to consider along the direction of existing current. Okay, so component of area has to be taken along the direction of current as well. So in this case, since the area vector as well as the current, they are in the same direction. Area is in the same direction, ds cap, and the current is also in the same direction for this cross-section area. So for this cross-section area, we will define the value of current density J, the mod of that, as Di over ds. But this ds is along direction of current. So in this case, this direction of current and the direction of cross-section area, they are parallel. But what about this case? Like in this case, if you see, I have taken the direction of area, which is not along the direction of current. Current is still flowing in the same direction. So in this case, when you will calculate the current density, this angle let's say is theta. In this case, if you will calculate the current density, to calculate the current density, you have to take the component of this ds along the current, and the component of ds along the current will be ds multiplied with cos theta. So for this cross-section area, the current density will be equals to Di upon ds cos theta. It's like this value of ds and this value of ds will not be same. As you can see, the cross-section area here and the cross-section area here will be different. Here the cross-section area will be a little bit more. So let's call it S dash dash. So that's how you define the current density. So while calculating the current density, the magnitude of current density will be equals to the current divided by the cross-section area in the direction of current. And this direction of current density, direction of J will be along the direction of current. Since this current density is a vector quantity. So that's how we define the current density. So in one case, the area vector will be in the same direction of current. There we don't have any trouble. We can just take the ratio of current divided by area. If at some places the area vector is not in the direction of current, in that case we have to take the component of area along the direction of current, and then we can calculate the current density. Or if we want to calculate this current and we have the density, we can just multiply it. Because you see, in this relationship, if you want to calculate the current, the magnitude of current, it will be mod of J multiplied with ds. You just have to multiply the ds, but again here also this ds is along the direction of current. But if you want to calculate the current from this relationship where the area is not along the direction of current, you will have to multiply the mod of J with component of area vector along the direction of current, and you will be getting the value of current after integrating it, obviously here. So that's how we calculate and define the current density. Okay, thank you.